Like we're just about there, folks. Welcome back, everyone. Definitely been a long break. I can feel it behind the tiredness in my eyes, but we'll get through this together. Any questions to start us out after the long break? Okay, well, what did we do last time? I believe last time we finished out chapter 3, so congratulations on that. That's a pretty long chapter we got through. We finished working on logarithms. So now we're opening a new chapter. We're not going to take as much time in chapter 4. Our main goal is to look at some interesting applications. And 4.1, 4.2 are just to get us started, get into the right place where we can look at those applications. Then we'll be looking at optimization in section 4.4, and before long we'll be in chapter 5. So exam 3 is going to involve portions of chapters 3, some of chapter 4, and potentially a little bit of chapter 5 as well. It seems like it's all over the map, but it'll be about the same kind of exam that you saw for exam 2 in terms of length. Well, other questions at the moment, folks, about any of these announcements? Okay, I had to think about a couple of things because we put the week on, or the class on pause for a whole week. We didn't assign a quiz, so there's not going to be one due Wednesday, but I'll have another one provided down here when we come back on Wednesday's class. Aside from the further announcements, our third exam is about 3 weeks away from today, so we still have some time before we're getting there. But I'm going to try to get information posted a little bit earlier than I have in the past. So I'll start trying to get information posted for this right around in the middle of this week or so. After that, we'll have, well, this is, if we look at our bigger Moodle website, we'll have a couple normal weeks right after, except for this one, we'll have review on our Wednesday. Then we'll be doing our Monday final exam, April 29th from 8 to 10 p.m. So that's going to be our plan for the rest of the semester. Still 6 weeks of stuff to get through, but we're definitely getting there, folks. Any other questions about where we're at so far? Okay, well, let's jump in then. So what we're doing is pretty much section 3.2 again in a really real sense. The big takeaway with section 3.2 is not so much taking a function like this right here and trying to graph its derivative. I mean, that is still important, and it was part of some of our work. But what was really interesting about this section, we're talking about maximum and minimum values, is the observation that whenever you have a minimum right here, this is considered a local minimum, that's when the derivative was 0. So we went from here to a 0 derivative in this location. Up here we had a local maximum. Well, the derivative was 0 because the derivative is equal to the slope of this tangent line. So we have a derivative of 0 as well. Then at the local minimum, once again, we have a 0 out derivative. And that's what's most interesting to us. Again, wherever the derivative exists and it comes out as 0, we expect to find a local minimum and a local maximum. That's kind of how we're going to try to optimize problems to find the least amount of something or the most of a certain quantity. So to get for the feel for that, we're going to just start with the core definitions of maximum and maximum values. Then we'll look at local minimums, local maximums. This one's a little bit tougher, but we'll go really carefully. Then from then on, the rest of the notes, it's all about trying to find the local minimums, local maximums. The critical number is going to be a big part of the homework, and the closed interval method, it will be as well. I'd say those are the major things that we're trying to take away. And everything above in the notes is more get everyone on the same page kind of stuff. Let's take a look, starting off on this problem right here. I have the definition written with the color coding that makes sense to me. And the yellow is going to be always the thing that's surprising. So for our first definition one, we'll say f of c is an absolute maximum if f of c just exceeds f of x for all x in the domain D. And when we say all x in the domain D, this is what allows it to be an absolute. The fact that we said every single x in the right domain. Likewise, f of c is an absolute minimum. With the less than sign, we're saying if it's below or less than every other f of x value in that same domain. So that's our meaning of absolute minimums, absolute maximums. Sometimes they're called global maximums or minimums. I don't use that language as much, but if you're doing the reading, you might see that here and there. If we want to talk about all of these at once, if we want to say absolute maximums, absolute minimums, all in the same sentence, we refer to them as just collectively extreme values, absolute mins or maximums. That's our definition. It's a pretty standard one, but it's honestly kind of technical when you see this part right here, the inequalities. But visually, it's way easier to spot. So I'll start with the minimum first and go to maximum. No, that doesn't seem right. Let's do maximum first, then go down to minimum on each one of these graphs. So when you look at these functions, they're all y equals x squared, but it's in fact 4 different functions because a function comes with not just the formula for calculating, but also the domains, and the domains have changed on every single one of these. So it's up to us to see what will happen to the maximum values and the minimum values. Starting with this one, although it's not conveyed, sometimes I put up arrows on these things because it reminds me the graph is still going up and up and up. And that means this function right here for y equals x squared, this has no absolute max. I'll shorthand absolute to just ABS. And max, pretty standard to just say max. Well, if a function is always increasing, then you can never get to some function value, f of c, that's larger than everything else, because just take your x somewhere else and you can exceed that value. Take x further off to 2, for example. But this one does have an absolute minimum. It's right here at the bottom of the graph. So we can say the absolute min is equal to f of 0, which is 0. So we have a minimum on that graph there. What does that make sense to folks on min and max for that one? Okay, and just to convey the shorthand, I'll say ABS min, just to stand for absolute minimum. And when we go to this one, well, some of the situation has changed. It still has an absolute minimum at 0 right below here, so that we can copy that down and say the absolute minimum is f of 0, which equals 0. But now we have a closed domain this time. That means when we go to the right, and we can only go to the right on the solid portion here, there's a value that's larger than everything else, and it's this one. The value of 4. So we can say this has, or the absolute max equals f of 2, which is equal to 4 on this one. Plus 2 down. Let me see if I can fit this just a little bit better. Don't necessarily want all these to kind of overlap. There we go. That should help me out, a little bit of guidelines. Well, any questions at the moment, folks, with any of these two graphs? Okay, one thing I wanted to mention is the way I'm writing these down has a lot of detail. I said the minimum is f of 0, which equals 0. The purpose of putting the 0 right here is just to say, where does the minimum occur? But the actual answer is always the output. So this is the answer we would give, 0. And there's not any real issue of a mistake, right? The input was 0, and so is the output. But over here, it does make a difference. The absolute max is not 2 on this problem. When we say absolute max, we're always talking about the y-axis. The actual answer, if you're doing, say, a WebAssign problem, would be the value of 4. Even if you took off this, I'd be okay with that because you're saying the right thing. The absolute maximum is the value on the y-axis of 4. I only put this in just for the sake of notes. We know we got to the maximum. This is the address. You put in a value of 2 to get to that value. So I'll highlight these in yellow just to emphasize this is what we're really going to put in for the answers. Well, any questions, folks, to this stage? Okay, well, we're on part 3 already. And looking at the domains, there has been a change. This is a closed set. The bracket is saying 0 is really in the domain. And that's why we're able to output a 0 for the minimum. A bracket here at 2 says 2 is in the domain. And that's why 4 was achieved as an absolute maximum. But something went wrong on this one. It's open on the left with a 0, but closed on the right. And this does have ramifications for us. We like the closed set because if there's a bracket here, it means 2 exists in the domain. And the solid dot is also telling us that that's a real point on the graph. We can say here, the absolute max equals f of 2, which is equal to 4. So same thing as before. Let me just fix that formatting. But now when we go down to this value for absolute minimum, going down below here, anyone see what you should write down for minimum? Kind of tricky in a way, I'd say. It turns out, and let me know if this feels weird, because it always kind of does when you look at this, especially the first few times. This one has no minimum. If it did have a minimum, it would be right at 0, inputting the 0 value. But that open circle there is because 0 is not even in the domain. In other words, f at 0 is undefined. We can't even calculate that value. In this situation, it also means there is no absolute minimum. None whatsoever. Kind of unfortunate in a way. Here's another way to think about this, though. Let's throw Desmos into the mix. I feel like this is kind of a confusing enough response on this one that we should support it with some graphics. Let's throw in y equals x squared. That's not the right graph, so we also need to convey the domain. I have to do it as a set. It goes like this. 0 less x less than or equal to 2. Oh, that's not quite right. There we go. That gives us the right set, and so we can zoom in on this thing. And notice what happens when you try to find the minimum. Finding the minimum means get closer and closer to 0, but I can't go to 0. It just hits undefined. You have to move to the right a little bit. At 0.08, we're at 0.006. That can't be the whole story, right? Because if you zoom in on this, you can get to 0.07 and maybe 0.064. It dropped down to a 0.04. And this game that we're playing here can continue forever. You can just get closer and closer to the 0, making the second coordinate, which is that 0.001, also go lower and lower and lower, but it never stops getting lower. Sure, there's a lower bound of 0, but this just gets closer and closer to it. That's a lie right there. Let's zoom in. You can get closer and closer to 0 as you like with, well, it's rounded to 0 there, but just keep on zooming in and you'll see it really isn't 0. You're just getting more and more precision the more you zoom. So that's the weird thing that happens when you put an open parenthesis right there. You can get arbitrarily close to 0 on the x-axis, which means you're getting arbitrarily close to 0 right here, but you never actually hit it. There's no minimum. This is a related concept that we had to fight with before, so let's throw this on there. Even though there's no minimum, we can still say that the limit as x tends towards 0. Now, this is an undefined statement already because my domain doesn't have anything on the negative end. The only way you can approach 0 is from the right-hand side. So we have to put a plus on there. So the limit as x goes to 0 from the right of x squared. In the limit, that one would come out as a value 0 because that's the value we're approaching as x gets closer and closer to 0. But this is different. If it's asking for an absolute minimum, you actually have to hit the value 0, not approach it in the limit. So that one's definitely tricky. Any other questions, folks, on part C there? Okay, and same issue on the last one. This one is a fully open set. And for a function that's always increasing on a fully open set, we would say for this, there is no absolute max and no absolute minimum. So that's the trickiness when it comes to absolute maximums, absolute minimums. We have to be really careful with the set itself because that causes a lot of havoc. We did it, folks. That's our first example after the break. I feel like I'm waking up ever so slightly. Any questions at the moment? Okay, So when it said all x in the domain D, this was the domain D that I was referring to, here, 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 and here. But maybe shouldn't use too much yellow color coding. Other thing I want to convey here is the answer is the output. So when we say absolute minimums, absolute maximums, we're not talking about the input of 2 right here. We're talking about the output of 4. Let's just throw in some arrows just to safely convey that as well, because there's not too many arrows to point at, but there they are. So that's the world of absolute maximums, absolute minimums. It is tricky in its own because of issues with open sets in your domain. But what gets really weird is if we say local minimums, local maximums. Here's where we'll spend a little bit more time and go really careful on this problem. So what makes it a local maximum is not this portion. This is the same. It's a maximum because f of c, the function value, the output, exceeds all the other outputs, but not for every x in the domain. We say when x is near the value of c right here. The nearness is what makes this local. Near makes these local, which makes sense. By local, we just mean in the nearby vicinity, but that's not good enough for us in mathematics. We need to be a little bit more specific about that. So our author did this in a kind of an interesting way. This is the qualitative way we think about definition 2. But if we ever have to be more specific, this is what he means by near C. We say something is true near C, we mean that it is true in some open interval, AB, you have to take your interval around that value, that contains C in question. So this will come into effect. Let's put a star on it. Right here. That's probably the most confusing end of this entire graph. And it goes along with this warning right here. Turns out there's never a local maximum or a minimum at an endpoint in the domain of a function. So nothing's going on right here for local minimums, local maximums. That's still easy to miss. We'll use the definition above to show why there's no local min or max right there. Well, that's the problem. Let's take a look at it and with a little bit more zoom and go through it very methodically. Well, I think a good way to organize is just run through it left to right and see what we can spot. So starting on the left here, on this first value, there's an open circle right there. And that means the domain D, let me write it this way, the domain of F is D equals, we go to the X values for the domain and it starts at a 1, but because of the open circle right here, 1 is excluded. So we'll use a parenthesis to say 1 is not actually in the domain. That's just where the lower bound is going to be. Then it goes off. This is defined at 2 because of the redefinition here. There's no missing values, so it ends at, well, let me put in some numbers. Ends at 7 with a bracket. Might as well do the y-axis as well, so we don't have to count these up every single time we look at it. So there's our domain. And now starting again on the left, we'll say that there is really nothing going on here. Let's say at x equals 0, there are no extreme values. All because of that open set. Sure, it's getting higher and higher, but it's getting higher and higher without ever really stopping. There's a bound, but the bound is not in the domain, and so we call that no extreme values in this situation. Does that make sense to folks so far with what happened at x equals 0? Okay, then continuing on, we move through the graph and then we get to this position. Something is happening at x equals 2 for sure, so let's write at x equals 2. And now here's the strategy I would probably take for this real problem. I'd probably get like 2 note cards, 3x5 note cards. If we're interested in 2, then we only care when x is near 2. So here's how we convey it. We don't care about anything happening on that side of the graph, nor that side of the graph. We just want to be near 2. We could put an open set conveyed by the yellow highlighter near 2, or if we can draw it in temporarily if we like. And this is what we mean by near 2. If we're in the vicinity of nearby 2, that function value by the red dot, would you call that a minimum or a maximum? Definitely looks funny how it's redefined, right? It like drops down in one spot. Hey, volunteers over Zoom, min or max at that value right here?
Minimum.
I agree, that looks like a minimum. And even if that red dot was kind of just say not there and it looked like this, it would still be a minimum. It's just a weird looking one. It always feels weird when we lose continuity somewhere, right? So bring back that graph. We've lost continuity, but that's okay. We have a local minimum because if we're constrained to this region of the graph, that is the lower value. The FFC is 2 right here. So at x equals 2, f of 2, which equals 2, is a local min. Oh, and sorry, I missed the chat. Yeah, absolutely. That one would have been a minimum. So that's the meaning of local on this one. Any questions, folks, on how we spotted it? Okay, well, let's go off to the next one then. Bring back the graph, and that was a weird problem point, but when we come up here, we peak out right in this location. Right in this location, that's where we would have said there's a horizontal tangent line. The derivative is 0 right here, but it's also, well, if it peaks like this, that's a local maximum. It's not an absolute maximum because this function height is at 4. There's other function values that say 4.5, 4.7, 4.9, 4.999, and so on. But if you restrict the graph like this, so all you care about is nearby 3, here's that open set around 3, then yeah, that function value at height 4 is considered a local maximum. So let's write at x equals 4, we have that f of 3. Oh, sorry, let me try again. At x equals 3 is what I wanted to start there as a statement. There we go. I think we're back on track. So picking the right value at 3, we look at f of 3, which outputs over here to a value of 4. So that value 4, the height to this point, is a local max. So that's the name of the game so far. We just need to look at the other problem points. So let's see where we're getting to. So next. Oh, didn't want to necessarily erase 3. There we go. So at 3, it was a peak. Then we come down to this one right down here at 4. And this one's a pretty interesting one. Would you say it's a local min or local max just by visualizing it? Yeah, go ahead.
Wouldn't it be a local minimum?
Yeah, absolutely. If we look at that point right there and simply restrict our attention to this part of the graph, I mean, we can have a pretty large open set. And that large open set, that's the minimum value. So we can now say at x equals 4 now, f of 4, which is equal to 1, is a local minimum value. So we're almost done with this one. Let's move down the line next. Weird Control Z deletes thing, restores whatever was deleted in a very weird order. Let me put that back. So at 4, we had a local minimum. Then we go over to 6, and it peaks off again. That one's going to be a local maximum. At this stage, let's just grab it and say we have a local maximum at x equals 6. f of 6, which equals, we take that function value here and output 3. 3 is the actual maximum, is a local max. So next, we go over to this one right here by the star, and this is where things go a little bit awry. The height of this point right here, well, if it was down this location, we would have called it an absolute minimum. It's okay for an absolute minimum to be on the end of a domain, as long as it corresponds to a bracket, but it's not a minimum, and you might now next look at it from this point of view. If you restrict your attention like this, it starts to look like a local minimum, except it's not. We really have to follow this portion in yellow. If it was a local maximum, the value of C that we're taking a look at is 7. So near 7, we have to have some open interval containing 7, and it almost looks like we could do it. Our interval could go like this, go from 6 to, but then we have a problem. The maximum you could put in there as an open interval is 7. But then it doesn't contain 7 if you write down an open interval like this. 6, 7 purposely excludes that 7 right there. So this is one of the weird technicalities in math. It has its purpose, but tracking the definition is tough. I would say this is just a good cautionary tale. And it's only about local maximums, and let's put here specifically, just to be really specific, nor local minimums. I'll put that in red since that was an addition out of nowhere. Now this one seems like it's left out. Put both red so they both seem important. So local minimum, local maximum can never occur at this boundary. So that means the best we can say is at x equals 7, no extreme values. Well, we did it, folks. I feel like this question right here is pretty tough. So if you're like me, you might feel the same way. It's a good one to come back to and try again, I'd say. But any questions at the moment? Okay, I want to add just a little bit more to this. And so just to make sure this one doesn't get too busy, let's take a really quick screenshot. I just take another view at what happened on example 2 before we look at things like extreme value theorems, Fermat's theorems. This is the purpose of all that stuff down below. So back to this one, if we look where we found a local minimum, local maximum, certain things happen there relative to the derivative. Let's take a look. At the very first one, x equals 2, we have no continuity right here. So at x equals 2, f prime at 2 does not exist. All because of a loss of continuity. It's a removable discontinuity, but it's still enough to break differentiability. So the derivative didn't exist there, and we got a local minimum. Let's look to the next one. At x equals 3, we're at this location, but here the derivative exists and we can calculate it. There's a horizontal tangent line, so the derivative of f at 3 should be 0. So let's write down at x equals 3, f prime at 3 equals 0. And we found a local minimum at height 4 when x was 3. So it looks like there's something interesting happening. We're spotting a local minimum where the derivative didn't exist, and where the derivative is 0. Over here, the derivative also doesn't exist due to the corner in the graph. On the left-hand side, the slope is large negative, and then on the right-hand side, it suddenly flips. The slope is large positive coming in this way. The derivative needs to be continuous, so this lack of continuity right here tells us at x equals 4, f prime of 4 does not exist. Let's be more specific because that's a challenging one. Let's say due to the cusp. Cusp being this shape right here that looks like something you could cut yourself on. A derivative has to be a nice, continuous, smooth curve. So spotting this tells us non-differentiability. But that's where the derivative didn't exist, and we found a local minimum right there. And same kind of pattern on the very next one. On the last one, which occurred at x equals 6, we have a point right here, another horizontal tangent line. And so at x equals 6, f prime at 6 equals 0. And right there, we found a local max. So chapter 4 is all about finding local minimums, local maximums, absolute minimums, and absolute maximums when we can. These are also particularly important to us. And notice what happened at every local min, local max, either the derivative did not exist, or it came out as a 0, and that's not a coincidence. What all this tells us is, we're going to try to optimize things. These are the things we should look at. We should calculate a derivative, find out when it comes out as a 0, or find out where it does not exist. Those are the first places to look for if we're trying to optimize, because all of those locations corresponded to the things we want, local minimums or maximums. What any questions, folks, with that second view of this problem? Okay, well, next, we're going to take a look at a couple definitions and theorems. They're important definitions, but they're mainly to try to direct us to the end goal of this entire notes, finding critical numbers and using the closed interval method. You'll notice the closed intervals were really important in this section. But before we get there, the next portions are just kind of organizing thoughts. First is the good old extreme value theorem. Let's hide Fermat for the moment. With the extreme value theorem, it tells us if f is continuous, on a closed interval, I was trying to put that in yellow. Let me try again. If we have continuity on a closed interval from A to B, then it's a guarantee at this point. There's no mathematical way to avoid this. F will attain an absolute maximum, and it will attain an absolute minimum somewhere. For some numbers, C and D, in that closed interval from A to B. So that's kind of impressive. It turns out continuity and a closed interval go extremely hand in hand when it comes to calculus. And we're going to later on see in chapter 5, just as a preview, a function is integrable. We're going to integrate functions later on, and we'll say a function is integrable if it's continuous on a closed interval. So if we have continuity on closed intervals, suddenly we're getting to the next concept of the course. That's going to be our integrability. This is such an important theorem that I thought this is a good one to just park here for the moment and get a feel for what this is saying and why it's so true. So the first thing I'm going to do is write down a function where we take off the things in yellow one by one. And that's a good way to analyze a theorem like this. It's really a very visual theorem. And somehow both of these conditions are necessary. To really get a feel for why it's necessary, let's eliminate them. For the first one, let's say f is not continuous. Now, we're not trying to prove the theorem, we're just saying what can happen to this theorem. If f is not continuous, and we still have a closed domain from A to B, here's about what the picture will look like. Putting everything in quadrant 1, just so it's a simple picture to look at. So it's not continuous, but I still have a closed interval. A closed interval implies I have to put a solid dot right at A, a solid dot right at B. I can't put an open circle any longer. But because f lost its continuity, well, what am I trying to do? I'm trying to show it doesn't have to have an absolute maximum, nor an absolute minimum. I'm trying to show we broke the whole theorem the moment we eliminated continuity from it. Here's how we can do it. First, let's do a couple just experimental draws. I'll use the pencil tool when I'm about to delete it. If I go like this, well, it is continuous, and observe absolute minimum probably here, absolute maximum right around here. I need to make it discontinuous, and here's one way to do it. Let's put in some value that gives this. A vertical asymptote is the thing that goes wrong really terribly. And I can make the curve go this way. We're allowed to do that. Plenty of curves have an asymptote approaching that way on that one end. And this end of the curve might go like this, upwards on that end. Now looking at this point, that's not a minimum, excuse me. Well, no, it isn't a minimum because there's other values lower. It's also not a maximum because on this end, these values are higher. Likewise, this one's neither a minimum nor maximum. This one has no extreme values at all. They just get larger and larger negative on this end, larger and larger positive on this end. So we'll say here, there's no extreme values. That's all because we took away continuity. Does that make sense to folks on what went wrong on that one? Okay, well, it tells us continuity is part of the secret to why this works. And we have a good idea what happens if we take out a closed interval, but let's do it just to illustrate. So for try two, let's say F has domain AB, which is open. In other words, we have an open interval that we're doing this on. So let's put down an A, put down a B. And because it's an open interval, I'm going to start my A with an open circle. We have to now. And B will have an open circle. I'm putting the heights pretty much randomly. Now next, I'm going to use the pencil tool. If I go like this, if it's strictly decreasing, that one actually works. There's no absolute maximum here. The curve just gets higher and higher. There's no absolute minimum. You can get lower and lower. And the moment you think you have an absolute minimum, I could get you closer. Just scoot X closer to B. So this one would actually do the job. If you drew something like this, though, I'll delete this one in a moment. This one is actually okay. There's an absolute maximum here, an absolute minimum down here. And that didn't contradict the theorem because the theorem is just giving a guarantee. So if I take out that curve, here's where the guarantee is actually violated just by making it go strictly down. Now there are no extreme values. And again, the thing that went wrong was it was allowed to have no extreme values, all because of the open set right here. If you made that a closed set, we would take away that possibility. And that's the content of the extreme value theorem. You make that set closed with a continuous function, and you will get a maximum and you will get a minimum. You could definitely test this. It's almost like a challenge where draw down a graph that has continuity on a closed set and try to draw it so it doesn't achieve a maximum or minimum. Let's do it ourselves. Let's say F is continuous on a closed set from A to B. So now we have, oh, didn't need to do that. Now we have everything we need on this one. Whoa, that was weird. There's all sorts of weird things you can do with this. We have a closed set and we have continuity. And so this will be our last look at this. We're going from A to B. I'll put a solid dot right up here. Solid dot way down here. You can change your graph if you'd like and put those dots anywhere. But as you go to write the curve, because we said it's continuous, you can't lift up your pen or pencil any longer. Because we said it's a closed set, these have to be solid. We can't get around this kind of tricky problem this time. And there's a lot of things you could try. We're trying to see if there's any way to not have an absolute maximum, absolute minimum. So if you want to make this one, say, not be an absolute minimum, you'd have to make the curve go down. But now it's an absolute maximum, so you can make the curve go up. But there's continuity, your curve has to eventually come down and hit B. Then look what we found. Right at this location, even because it's an endpoint, it's okay. This would be the absolute minimum. It could never be a local minimum at the endpoint. And right up here, when we turned around because we had to, I'm not sure if maybe that's slightly higher. This is the absolute max, gives us some value here. The absolute minimum gives us some value here on the y-axis. So that set, or this idea right here, is extremely valuable for us on finding absolute maximums, absolute minimums. Any questions about that so far? Okay, so we're later going to turn this around and look at a so-called closed interval method. The closed interval method are looking for other things. We want to also take a look at critical numbers. And here's the rundown on a critical number. A critical number satisfies this condition. The derivative of f prime at c is equal to 0, or it could be something where the derivative might not even exist. But first, Fermat's theorem itself says, if f has a local maximum or minimum at c, and if it turns out the derivative does exist, it must be the case that the derivative is 0 right away. So this is the major content of Fermat's theorem. That's a wonderful theorem. It says if you can find and solve this right here, you might have found a local maximum or a minimum. But the way I said that is also unfortunate, because this is the way the logic goes. It's P implies Q in a certain sense. P is the hypothesis, and it's this entire portion right here. So this is the hypothesis P. So it comes with two statements. F has a local maximum or minimum, and the derivative exists. This is the Q, which is the conclusion, Q. And the reason for writing all of this is the logic goes in one direction. And this is really kind of unfortunate sometimes. You have to satisfy all of your hypotheses on P to satisfy Q. And this means Q implies P is false. This is considered to be the converse. What makes it a converse is I took the arrow, P implying Q, and I switched it around. What the converse would read is, if the derivative is 0, then f has a local maximum or a local minimum. It's really unfortunate that that's a false statement, and this example below is the counterexample to that. Fermat's theorem is still useful because it tells us wherever the derivative is 0, that's the first place you start to look. But it's not a guarantee you actually have a maximum or a minimum. You have to start with all of this as being true to guarantee the derivative is 0, but then you can't go backwards in that entire statement. Here's a function. Let's see just how it works with this one. It says here, examine the function f of x equals x to the 5/3 power. We wonder, does f have a local maximum or a minimum at 0? Well, following this process, let's see what would happen if we tried to reverse and look at the converse. We're going to look at the Q statement, which is talking about a derivative. So first thing is first, let's take f prime of x. We'll just use the power rule. 5/3 comes down. The new power of x is 1 less. So take 5/3 minus 3/3 to get a power of 2/3. And we did this portion right here, the f prime at x portion. Next, we're going to set it equal to 0. And just to correspond what we're doing, we're now at the right end, the Q part of Fermat's theorem. And that's just an equation we could solve. And what we're trying to solve for is that, the input that gave us the value 0, the critical number C we'll later call it. That's a pretty fast equation to solve, though. You could multiply both sides by 3/5, and you get x to the 2/3 equals 0. But even that was a not necessary step. The only way this equation is true for real numbers is if x itself is 0. So there we have it. X equals 0 is the C in Fermat's theorem. But this is dangerous, right? We're reversing an if-then or P implies Q statement. We're starting with the conclusion and hoping the hypothesis is true. It turns out it's not. The hypothesis says f has a local maximum or minimum. Let's take a look at the function and see if we can spot it. That's way too big. Let me try again. I'm probably going to need to reset this domain. Let me just see if scrolling is going to work for it. That should work, just a bit of a mental break. The function goes f of x equals, now I'm not plotting this one. This one's the derivative. The question is about whether the original function has a maximum minimum. So we go to the f of x on this one. X power 5/3. This is what the function looked like. And we did the derivative right. We solved it right and got a 0. But notice there is no minimum or maximum. The function just continues to increase. We did it right. There is a horizontal tangent line, because if you zoom in on this, the whole curve is going to look more and more horizontal. You can make it as horizontal as you like by zooming in on 0. But it's pretty clear that this function has no minimum nor maximum. Let's put that down on the paper. So there it is. And this is the last portion about our analysis on Fermat's theorem. We're looking at this. If there's a local minimum or maximum, and there is none, we can say here, there is no local min nor max at x equals 0 here. In other words, the statement P turned out to be false. Let's say it this way. P is false. So that's unfortunate. It's still an important theorem, but the downside is everyone wants to work it from the right-hand side and get the conclusion on the left. But mathematically, it can't be turned around like that. The converse turns out to be false. We'll still collect some ideas from it and develop an idea called the critical number next. But any questions at all, folks, with the analysis of Fermat's theorem? Okay, so riveting stuff. Again, Fermat's theorem is just illustrating an idea for us, what we're all trying to get to. Notice magical things happen whenever the derivative is 0, or whenever the derivative just fails to exist, like in our earlier graphs we were taking a look at. We put all of that together, we get this next definition. I highlighted this one in yellow since this is a very important definition to chapter 4. It's something you'll see quite a lot. A lot of problems will just say, find a critical number. Or for farther along into chapter 4, a lot of problems start, like the very first step you do is you just find the critical number. So a great way for partial credit on exam 4 is doing this. Calculate a derivative, set it equal to 0, and solve it. That's one way to get a critical number. The other way is when the derivative does not exist. So that tells us we're looking at where the derivative is 0 or where the derivative does not exist. We're looking at the specific locations where we could find a local minimum or a local maximum. In other words, it's really just this all over again. We have local mins and local maxes whenever derivative didn't exist or come out as a 0. So because of this picture here, and in part because of Fermat's theorem, this is the major thing we start to focus on, finding critical numbers. And because this is kind of easy to miss sometimes, keep in mind there's two things to look for when the derivative comes out as 0 or when it doesn't exist. This portion here doesn't come up a lot, but when it does come up, it's extremely confusing. So I did put some in the notes for us to try to find. Well, once we get through critical numbers, we're going to put everything together into an overall method called the closed interval method. But this is the first step, find the critical number. So we might as well practice right here. So first step is, when it says find the critical numbers of the given function, you'd want to do this right away. Step one, calculate f prime of x. And that's nice. That's what chapter 3 was all about, just taking as many derivatives as possible. We're starting off with a nice polynomial function. So the derivative will go 3 x squared. From here will be a minus 6. And that's it. That's our first derivative. So step 1 is done. Sometimes people combine all these steps into just one major step and write equals 0 right here. If you want to go in order, here's the next thing to do. We're still looking at when f prime of c equals 0. So we take this, 3x squared, minus 6, set it to 0 and just start solving that thing. Add 6 to both sides to get 3x squared is 6. Divide by 3 to get x squared is 2. Then the last thing to do is just to take square roots of both sides. We'll get x equals positive or negative square root of 2. So these are the critical numbers of f. So we did it. It's kind of like a chapter 3 problem where you do step 2, where you're solving the equation right immediately after. And you know, I did notice on a lot of work, whether you were doing a quiz or doing an exam, a lot of people took answers like this and they factored them. Good call. When you're finding critical numbers, sometimes factoring is the thing that you must do. So we'll start factoring our derivatives with this in mind as we get further and further into chapter 4. This one didn't need a factorization because you can isolate x squared was the only reason. Don't like that too, though. Let me fix that one. Well, any questions at all, folks, on finding the critical numbers here? Okay, notice I completely ignored this portion where f prime of c does not exist. Reason we got away with that was this, as a derivative, has no issues. There's no way I can put in a value that's going to cause an undefined. The domain is all real numbers implied. And so we can say here, f prime of x exists for all x, meaning we are not going to get a critical number because the derivative failed to exist at a point. But this one might have an issue right at -7. The function itself doesn't exist at -7, so we might have a same issue here. But if you take another look, a critical number of a function is a number c of the domain of that function. Well, -7 is not even in the domain of that function down there. And so it looks like we won't even pick a critical number from that one as well. Thought I baked one into the notes, but I don't think this one is even coming up on the notes at all. But still, it's good to watch out for those problematic points. And let's try this out all over again. Same instructions, we're looking for critical numbers. On this one, we have to hit it with the quotient rule. So we'll start off by just going f prime of x. And we've done quite a few quotient rules. Folks did really well on this on the exam. So let me see if we can get away with doing it this way. Once you do quotient rule more and more, it's not a bad idea to take a couple shortcuts. And this is how I typically calculate it. It's going to be the derivative of the top. So I'll put in as a 1, just because that reminds me we did the derivative of the top. Then you copy the bottom. I'm using black to say we didn't take a derivative. It's just a copy step. There'll be a minus. Then you copy the top, x minus 5. Then you multiply by the derivative of the bottom. That's a nice function. That derivative just comes out as a 1 as well. Then down below, you take the bottom and square it. I'll put that one as green just because that's an easy one to miss. The denominator is what gets squared. And that's our whole derivative. Now, we always want to simplify these things. And the reason we went for that is we're going for critical numbers. Some of them in the homework were really tough to simplify, but in chapter 4, they're all going to be very approachable because we have to solve an equation in the next steps. So the times 1 doesn't do anything here. We can drop parentheses, get x plus 7. Here, the times 1 makes no effect, but this negative sign does distribute through, so we'll get negative x. plus 5. Down below, it's a x plus 7 to the power of 2. And that means we have altogether 12 divided by x plus 7 to the second power. Well, we did it, folks. That's the first portion. We want to find a critical number. I'm at this stage. I took a f prime at x rather than an f prime at c. And if you want to combine steps 1 and 2 into one step, just take this portion where it says equal to 0. And you could do it right here as well. Just set it equal to 0, and we're going for the critical number right at this step. Well, this was a kind of a nice one to solve. The way you would probably solve this equation, let's just write over here to demonstrate. The go-to method here is just clear the denominator. You can visualize it this way. A cross product is going to feed that denominator to the 0, just eliminating it. Or you could go this route. Take x plus 7, multiply it into both sides. If you did it that way, you have a cancellation going. Oh, let me try one more time. You need to take x plus 7 squared, the actual full-on denominator. There we go. Now my cancellation works a little bit better. X plus 7 squared cancels with this one. And you get the statement 12 equals 0, which has no solution. That means there is no critical number. Doesn't mean there's no maximum or minimum, although that could be the case for this one. But it means we're not going to find a maximum minimum because of a situation where the derivative exists and comes out as 0. So we've lost all critical numbers in that way. Next, the derivative here doesn't exist at -7. That's true. But -7 is not in the domain of the original function, so it fails to be a critical number for that reason at the same exact time. The last takeaway on this part B, though, is we're going to solve a lot of equations that look like this, but notice all you really do is you immediately clear the denominator, and it only boils down to if you can set the numerator equal to 0. If there's no variable, it's automatically no solution in that case. So that's a shortcut we'll take a lot in the yellow highlighting, just focusing on the numerator, because this right here, clearing denominator, is always a foregone conclusion. Well, folks, that's finding critical numbers. Any questions at the moment with what we've done? Okay, so this is where the notes all kind of converge into one overall goal. What we're trying to find is absolute maximums, absolute minimums, local maximums, local minimums. And this next method gives us a way to find an absolute maximum and an absolute minimum. Let me put the word absolute here, just to be specific. Okay, so this method is based off the extreme value theorem that we were just looking at. It's based off critical numbers, so it's motivated by Fermat's theorem. And here's how it goes. To find the absolute maximum, absolute minimum values, you need a continuous function right away, and it has to be continuous on a closed interval. That's the reason I put the extreme value theorem here. That's exactly what this is saying. Continuous on a closed interval. This is a really, really powerful statement when it comes to real value functions. If you have that, the theorem says there will be an absolute maximum, absolute minimum, and the method here just tells you how to find them now without having to graph it. First thing you do is you find all critical numbers in step 1, evaluate the function at the endpoints of the interval, so f at a, f at b, f at the critical numbers. Then step 3, you're just summarizing. The largest value you found prior is your maximum, and the smallest value you found in step 2 is your minimum. Let's give this all a try and see how it goes. Any questions about the method at the moment? Okay, so every time you do this method, an honest closed interval must be provided. If it's not provided, the whole question is ruined. And so there it is. That's our closed interval from 1/2 to 2. We need a continuous function, but x minus natural log x, it would be continuous on that domain, so we're all set. And let's now go down the line. Step 1, we have to find the critical numbers of this function right here. So the very first thing we do is differentiate it. Right, f prime of x, and going left to right, derivative of x is a 1, minus, and it was a long break, so I understand if you're not sure on this derivative, but just for the sake of recalling it, that can be fun. Anyone recall how this derivative goes? Derivative of natural log x is, any volunteers? It was definitely a long break for me too, if I'm being completely honest. I didn't do too much work myself. Let's put down a couple reminders. The formula that is the most general one goes like this. This is the easiest one to forget as well, so it's probably the best one to start with. Derivative with respect to x of log base b of x. Let me fix that typesetting a little bit better. This goes 1 over x times natural log of b. So that's the general formula if you have something other than a natural log. If you do have a natural log, it goes like this. Derivative with respect to x of the natural logarithm of x. This one is just a 1 over x, so it's a kind of a nice derivative. So that means right here on negative natural log x, this one just converts to a 1 over x like that. Well, we did it, folks. That's our derivative step. Now, because in step 1, we're finding critical numbers, we also have to worry, when would this derivative fail to exist? You can't put a 0 there, for example, but the domain doesn't even include 0, so we're actually okay. This derivative exists for every number in that actual domain. So next thing we're going to do to find the critical numbers is just take your derivative, set it equal to 0, and solve it. So now we're solving this equation right here. I think a good way to solve it is just add 1 over x to both sides. So 1 equals 1 over x. Next, you can multiply both sides by x, which is just a cross product, really. X would come out as a 1, but be really careful once you get the value here. We must double check it's actually in the domain, and we're all set. 1/2 to 2 does include 1. If this was, say, a 3, and we're going from 1/2 to 2, we would have had to say no critical numbers right at this step. But we could say now x equals 1 is the critical number of f. Well, we did, folks. That's our step 1 in conclusion. At step 2, it's kind of just busy work in a certain sense. It says find the values of f at the endpoints and the critical numbers. That's just a whole bunch of function evaluations. Here's what it would look like. Let's call this step 2. Evaluate f at the endpoints. That would be referring to these. These are the endpoints of the domain. So we need to evaluate f at 1/2. So we're plugging 1/2 into this function, f of x. It'll be a 1/2 minus natural logarithm of 1/2. Then the next one is at 2, but I think sometimes it's kind of just flows, right? If we go to the next pertinent value, the critical number, shouldn't hide the step. So I have an endpoint. I'm going to grab the critical number next, just to take the inputs in order. So f of 1 is going to be equal to, throw a 1 here, minus the natural log of 1. Natural log of 1 is 0, so this is exactly 1. That's the one I can calculate exactly. Now we're going to the next endpoint, which is at a 2. So f at 2, and honestly, this is really tricky, and it only gets trickier in the chapters. When it says f of 2, you don't plug it into this one. That's one of the major reasons why I always indicate what I'm calculating, because in chapter 4, you'll have a function, you have the derivative of the function, and sometimes you'll have the second derivative of the function, and these values have to be plugged into the right thing. Good idea to start labeling them just so we don't get mixed up what goes where. So on this one, we're plugging 2 inside here, so it's 2 minus natural log 2. Now for some of these values, I'm not sure what they are going to evaluate as. So I'll do a couple quick approximations just to get a feel for it. So on this one, a half minus natural log of 1/2, that one's about a 1.19. And let's check out the other one, 2 minus natural log 2. This one's a 1.31 rounding. And so now we have the size of the magnitudes of things. This is f at the endpoint, at a critical number, and at the other endpoint. Now we just do step 3. It says the largest value is the absolute maximum. That makes sense. So let's say here, largest value was 2 minus natural log 2. What I'm going to do is say it equals the absolute max. Next, the smallest value is the absolute minimum, and that would be this one. A half minus natural log a half is just a little bit larger than 1. So this one, let's just do step 3 right here and say that's the absolute minimum. It feels weird to not put step 3. It just looks like we didn't do everything, so I'll put it here. Step 3 is just saying what we found. Let's also box it because that's where our answer is. The absolute minimum is 1, and the absolute maximum is 2 minus natural log 2. After you do a problem like this one, it's not a bad idea to just see how it comes together. See if we really got what we think we got. Let's plug in the function. F of x equals x minus natural log x. But you have to do more than just the function. You have to put in the domain as well, which will be a closed set. So that goes into Desmos like this. Curly brace, 1/2. Closed set means less than or equal to x less than or equal to 2. And let's see here. It told us that our absolute maximum should occur at an input of 2. At an input of 2, we got a 1.31 of rounding, so that looks about right. And our absolute minimum should be at an input of 1 or a minimum of 1. It actually looks like that's exactly what we said. And now we're not worried about doing this with a 1.307 because we found the true absolute max. It's not really 1.307, it's 2 minus natural log 2. That's the exact quantity that we're really going for. We did it, folks. That's the closed interval method. Any questions or comments about it so far? Okay. Well, that was so fun. I have a part B down here. But you know what? I think this one will take more than about 7 minutes and some change. It'll be a good warm-up to come back on Wednesday's class. We'll finish off this one right here and take a look at section 4.2. So this will be our last one for the day. Any last questions before we call it a night, folks? Okay, well, I appreciate everyone's hard work. It's tough getting going after a really long break, but we've got about 5 more weeks to go. We'll get back into the swing of things. If you have any other questions, feel free to stick around. Otherwise, I'll see you all on Wednesday. Have a great night, folks.
Thank you.
You bet. Have a good one.